So in this video I want to take you through some questions that are like some of the more difficult questions in 10F. And one of the ones that is surprisingly complex based on a very short question is question 11. So I've got an example here that mine has x cubed and a different point from question 11, but the process is the same. So find the point on y equals x cubed that is closest to the point 4, 0. And that's all it says. So to try and work this out, it's best to try and have a picture in your head of what it is that you are trying to find. So you want to point on this curve. So draw this curve first. Put a point, and we're just going to label it as x and y. And we want to know what that point is, what that is closest to the point 4, 0. So 4, 0 is going to be down here. Now this point could be here, 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 anywhere along this line. And what we're looking is, what is the distance between the point and 4, 0? So what is that distance? What is that distance? What is that distance compared to that distance, compared to that distance, which is 4, compared to that distance, compared to this distance? Where does the point need to go along this curve so that that distance is a minimum? So we want a minimum of the distance between the 2 points. So we need a distance formula. And we need a distance formula between these 2 points here. So let's have a look at how we'd go about doing that. Now the distance formula is not on the formula sheet. So you either need to remember it or you need to remember a way to work it out. So a way to work it out is if you have 2 points, one here and one here, the distance between the two of them is always a straight line. And then you can always make a right-angled triangle using the difference between the two y's. So this is y2 minus y1. y2 minus y1 gives you that distance. And this distance here is x2 minus x1. And you can use Pythagoras' theorem to figure this out. So our distance formula using Pythagoras, d for distance, over here, is d squared is equal to y2 minus y1 squared plus x2 minus x1, all squared. And then to find the d, we unsquare it by square rooting it, square root both sides. Those will cancel and you end up with d is equal to the square root of that. So this is the formula that we're going to use. And so to use that we need 2 points. And so I'm going to label my 2 points. One is a 1, one is a 2. So this is going to be point number 1. This is going to be point number 2. Now I'm going to substitute in my x and y values for 1 and 2. So the y value from point 2 is 0. Take away the y value from point 1, which is y. Now I can put a y here, but the equation of this line is that y is equal to x cubed. So instead of putting this as a y, I could put an x cubed there. And then I only have x's in my formula. I'll show you in a sec. Finishing off our formula, x from point 2 is 4, minus x from point 1, which is x squared. And so now I have a distance formula. D is equal to the square root of minus x cubed squared plus 4 minus x squared. And now I've got a formula. I can differentiate that with respect to x and let it equal to 0 and solve to find the x value that gives me the minimum distance, and then substitute that back into my equation for my line to find the coordinates of the point. So I'll go ahead and do this. If you press pause, you can try doing this and then check your answers as well. Okay, how did you go? You can see I've defined the function and solve for the derivative equal to 0 for x, and it tells me that that occurs when x is equal to 1. So that must be, I've only got one answer, so that must be the minimum. So the point that's closest has an x value of 1 and a y value, which is 1 cubed, which is 1. So the point that's closest is the point 1, 1. So this example is like question 12. So we have a rectangular field, and here is the nice green grass in the field, and someone is going to run, for some bizarre reason, from this first corner to the diagonally opposite corner at C. Now they don't have to run in a straight line to cross. They can run, jump the fence, and then run along some kind of road or something that runs along there that makes it a little bit quicker to go along that pathway there. So we've got two different speeds. We've got the speed that you can run, oops, let's get rid of that. Got the speed that you can run through the grass to some point, and then the speed that you run along the dirt. This is a common sort of question, and so what they're asking is, from here, where do you aim? Where do you aim along this fence line so that you get to C in the shortest amount of time? So do you spend more time or less time running through the grass, or more time or less time running along the road? Now, often the question will be put in terms of, like this one here, in terms of an angle that you head off at, and sometimes it's in terms of a distance between these 2 points here. But anyway, so this is like question 12. So mine has 100 meters as the width of the field and 500 meters as the length of the field. Whoever is running this thing can run through the grass at 5 kilometers an hour, but can run along the road at 8 kilometers per hour. And so the questions ask us to find the time taken to run from A to P. So that P could be anywhere along here in terms of theta. So as that angle changes, that length there will change. And then they want us to find the time taken from P to C in terms of theta. So we're going to find out that distance there. Then we're going to find the angle which gives the minimum time to run. So we need to find this one here. It says minimum time. So we're going to need a formula for time from A to C, to run from A to C. So we're going to need to get a formula for that. And then finally, they want us to find the distance from B to P, which gives a minimum time for running from A to C. Okay, so let's have a go at doing these things. So the very first thing we need to do is to find the time taken from A to P in terms of theta. So we don't have any kind of time measurements here, but we've got some distances and we've got some speeds. So we're going to go back to our Year 9 work on speed, distance, time and rates and use our speed, distance, time formula. So some of you may have used the little triangle that I have here for speed, distance and time, the relationship between speed, distance and time, and some of you may just be familiar with this formula here. It doesn't really matter which one you use. If you are using this triangle here, if you want to know the formula for time, you cover up time and it appears that what's left is a D sitting on top of an S. And so from there you can read that T is equal to D sitting on top of S. Time is equal to distance divided by speed. If you're working with the formula over here, you can multiply both sides by t, and that will cancel, and then divide both sides by s, and you'll end up with the same thing here. Okay, so we know that our time is equal to our distance divided by our speed, and so what we need to do to find the time from A to P, we need to find the distance from A to P. So let's grab a copy of the picture and have a think about what we've got here. So we're going from A to P. So we want to find this distance here. We know that that is 100 meters. We know that it's a right angle because we're told it's a rectangular field. So what we've got is a right angled triangle here. And so we could let this distance AP be our hypotenuse. Well, it is the hypotenuse of our right angled triangle, and we could use this angle here with its adjacent side and its hypotenuse to say that cos of theta is adjacent 100 over the distance AP. And then we can rearrange that formula, multiply both sides by AP. So AP times cos theta is equal to 100. So AP is 100 over, let's shift this up, 100 over cos theta. And we can put that onto our diagram if you like, if it helps you to understand what's going on. But we're not actually asked to find the distance, we're asked to find the time. So we're going to use our time equals distance divided by speed. So we know that when we run along here, in the question they told us that you could run through the grass at 5 kilometers per hour. So we have time equals distance over speed. Our distance is 100 over cos theta, and our speed is 5 kilometers per hour. So we can simplify this formula down a little bit. So this is 100 over cos theta, divide by 5, or times by 1 over 5. The 5 will cancel with the 100 to give you 20 over cos theta as the time that it takes from A to P. So this is part A. So for part B, we need to find the time taken to run the rest of the way from P to C. So we know that they can run at 8 kilometers an hour, but we need to work out the distance from P to C. Now we know the distance on the equivalent side from A to D is 500 meters. So this distance is going to be 500, take away whatever B to P is. Now we just found out what A to P was using trigonometry, and so we can do the same to find from B to P using trigonometry. And from B to P is the opposite side, and so we want to know what the opposite side is. We have the adjacent side and the angle, so we're actually going to use tan of theta to solve this. Tan of theta is the opposite side, which is BP, divided by the adjacent side, which is 100. So B to P is equal to 100 times tan theta. That means that from P to C, so this distance in here is 100 tan theta, which means the rest of the distance, therefore, from P to C is 500, take away 100 tan theta. That's our distance from P to C. Now we weren't asked to find the distance from P to C, we were asked to find the time from P to C. So our time is going to be equal to our distance, 500 minus 100 tan theta, divided by our speed, which was 8 kilometres per hour. And so this is the time from A to P, and this is the time from P to C. And part C asks us to find the angle theta, which gives minimum time to run from A to C. So to run from A to C, we need from A the total time. I'm going to put T of theta. T of theta is equal to the time to travel from A to P, which is 20 over cos theta, plus the time to travel from P to C, tan theta over 8. So that's our formula for the total amount of time taken. To find the minimum time, we're going to find T dashed of theta equal to 0, and we're going to solve that on our CAS when theta is equal to. So now we have to work it out. And so I've done some calculations on the CAS. Let's have a look at what I've done here. So I've defined my function, and then I asked it to solve for the derivative equal to 0. Now because I have periodic functions in here, I've got a general solution. So I just went back up and copied this down and said that, okay, I need a restriction for my angle. So I'm using x here instead of theta, by the way. So I need a restriction for my angle. And so my angle has to be in this rectangle. This is the angle here. So the largest the angle can actually be is 90 degrees, which is pi on 2. So the smallest can be is 0, the largest can be is pi on 2. And when I put that into my calculator, you can see that it told me an answer of some sorts. Now, the reason that it's giving me this answer, and you can see on the next line, I've actually got an approximate answer, is that in my settings, my calculation mode is set to exact. And calculation mode is, this one is exact, and this one is approximate. So if you get an answer of something like this, and you can't get your calculator, and I did try Control Enter, and for some reason it wouldn't work for me on my computer, and so I've actually went and I changed the settings, and then I redid the sum, copied and pasted, and then I turned the answer back. So this is our angle in radians that gives us minimum time. So this angle here, if I wanted to give this answer in radians, I would need to convert this to radians. So I'm just going to write this here, 6, 7, 5, 1, 3, that'll do. A few more dots after that. And then the final part in the question asked for the distance from B to P. And so the distance from B to P, all I've done, you can see, is I've substituted the answer in here. So I actually use the ANS button here on the CAS calculator rather than copying the information down. And you can see that it's actually added a couple of extra digits on the end of my number from what it had over here, just to give me a little bit more accuracy. And so the final answer for the distance from B to P, and I should have made the question say how many decimal places it is that answer there to however many decimal places the exam question will say. And I want to have a look at just one more question before we go. I know this has been a long video, but let's look at just one more. Now this is very wordy, and it is very similar to a style of question that we used to have in the past. You may or may not have heard about Tasmania Jones. He was a regular occurrence in the methods papers for many, many years, and Tasmania Jones has retired. But anyway, this is the sort of question that you would get, and see if you can see the similarities. The point B is 2 kilometres offshore from the point A, which is located on a straight beach. The point F is 10 kilometres to the right of point A along the beach. Tasmania Jones is in a boat positioned at point B and needs to get to point F as fast as possible. The boat is currently sinking. Tasmania Jones can swim at 5 kilometres per hour and he can run along the beach at 12 kilometres per hour. To minimise the total time, Tasmania decides to swim to a point X kilometres along the beach from A and then run the rest of the way, run the rest of the way to F. Find an equation for t of x, the total time taken by Tasmania to complete his journey. So you can see again, this is almost exactly the same as the other question. This time we don't have any angles here, but we still have a right angled triangle. We have 2, we have x, and we can use Pythagoras' theorem to find this distance here. So we can use Pythag on this. And if it helps to colour code things up, he is swimming from A to B, so that is the swimming thing. So that distance there along that Pythag bit is where he will be using his swimming speed of 5 kilometres per hour. And then he's going to hit the sand and he's going to run along the sand at 12 kilometres per hour. Hopefully you can see the consistencies here with how this would work. You can see the question continues on. Find the distance x that he should swim to minimise the distance. All the same deal, same sort of question. You'll see this over and over through the questions that you work through.